The past few lessons have focused very heavily on the importance of the nuclear particles. So the role that protons play is in determining the identity of the element, and the role that neutrons play is in determining the mass of each isotope. And every element, or at least most elements, have more than one possible number of neutrons. But some of them are more likely than others. So for example, most carbon atoms have 6 neutrons, and that gives them a mass of about 12, but a small percentage of them have 7 neutrons, which gives them a mass of 13. Okay, there are also some carbon atoms that have 8, but the difference here is instead of being given a percent abundance, you're given a half-life, which means that this isotope is radioactive. So our next few lessons focus on A, how did nuclei form in the first place, and then B, when they form, why are some of them unstable, and what happens to them if they're unstable. So to start off, we have to kind of go all the way back to literally the very beginning. And you'll have to excuse me, I am not a Big Bang expert, so this is going to be a very shallow overview. So if we discuss the idea of the Big Bang, it's that all of the matter and energy in the universe was contained in one small spot. It was really intense, and eventually it got unstable and it blew up. So the mass and energy all started expanding outward at a really, really rapid rate. Okay, and when we say matter, okay, we mean the bare minimum of matter. So you have to forget about elements for a second because there were no elements yet. Protons and neutrons are made of even smaller particles that are called quarks. And as this sort of quark soup, as they call it, started to cool down, the quarks collected in ratios that eventually formed the first protons and neutrons. So this picture over here shows you quarks have weird names: up, down, top, bottom, strange, and charm. So a proton is made from the combination of 2 up quarks and a down quark combining, whereas a neutron is 2 down and 1 up. Okay, so you don't really have to know that for honors chemistry, but I'm just trying to explain to you how the first elements actually started to form. So we had quarks, the quarks cooled down and started to clump into larger particles, and that's how we got our first protons, which is really, in a sense, hydrogen, because hydrogen is mostly just a proton. So the formation of protons and neutrons is really the beginning of the formation of elements. And the protons and neutrons go through a really similar process to what the quarks did. Okay, it's still cooling down. Okay, the big freeze out happens at 1 second after the Big Bang. And then gravity, starts taking over. The protons and neutrons start maybe clumping together. So we have the bare minimum of element, which is just 1 proton, and that's hydrogen. But we also have the isotope of hydrogen that has a neutron in it. Okay, and then maybe even something as large as helium starts to form, where 2 protons and 2 neutrons clump together. But we still don't have anything that we would consider massive or heavy forming yet. What happens first is all of these really small atoms, okay, slowly have to settle out. Okay, gravity takes over and they start to kind of clump together in really large clusters, which were the first galaxies. And then within the galaxies, okay, we have even denser concentrations of hydrogen and helium, and that is the formation of the first stars, which is where we actually begin to see the other elements start to form. So all of this hydrogen and helium starts clumping together in really compact units, which are stars, and that generates a lot of heat and a lot of pressure. And over time, this heat and pressure gets so intense that the hydrogen and helium actually start fusing together. So nuclear fusion is our explanation for how the heavier elements came to be. So we take small nuclei and we combine them into one larger nucleus. This diagram is showing you, every star starts with hydrogen. So if we have an isotope of hydrogen that's 2,1 and an isotope of hydrogen that's 3,1, okay, these 2 nuclei come together and they form a 4,2 helium. And then this little neutron, he gets left out by himself, but that's okay because he'll just go find some other atom to be in. So at their core, stars are element factories. Okay, they're so hot and they have such high pressure that they take small atoms and they start crushing them together into larger atoms. rather than always using a diagram to show this process, we use what we call a nuclear equation. So if we look at the way this is written, okay, we interpret it almost sort of like a math problem. Okay, you take this isotope, which has a mass and an atomic number, plus this isotope, which has a mass and an atomic number, and the arrow works sort of like an equal sign. So we're kind of saying hydrogen plus hydrogen equals, and we have a helium forming and then a neutron. So if we look at the mass, okay, we have a mass of 2 and a mass of 3, that's a total of 5. On the other side, the mass stays constant. Okay, it's reformed into 2 different substances than it was before, but it still has an overall mass of 5. On the left side of the arrow, the hydrogens had 1 proton each. Helium represents that those 2 protons are still there, and this 0 means the neutron is not taking a proton with it. And stars do not stop at forming helium. Okay, once they've used a lot of their hydrogen and now all they have is helium, they're going to start the same process over again, except this time they're going to take heliums and they're going to turn helium into something else. So this nuclear equation is showing you an example of that. If you take 2 heliums, which both have a mass of 4 and 2 protons each, okay, you can fuse them into beryllium, which has a mass of 8, or this particular isotope does, has a mass of 8 and has 4 protons. And the process continues. As we move from hydrogen to helium and then helium to carbon, we might end up with something as heavy as oxygen. And a star can take 2 oxygens, okay, we need a mass of 32 to be represented, and it might turn them into 1 atom of silicon and an atom of helium. So a mass of 4 gets left behind. Okay, then it just continues further and further and further. So as the star is using up all of the elements, okay, they start to get heavier and heavier. So we have neon and magnesium, silicon, and then eventually a star long into its life will start to form the last element that it can form, which is iron. So what is wrong with iron exactly? All of these other nuclear processes that have been happening, so if we go back and we look at this, one of the other things that they release is an enormous amount of energy. So as the atom is fusing 2 nuclei together into 1, it's also generating a huge amount of energy, which we're very thankful for because that's why life is able to live on Earth. So the heat and the light that we get from the sun is all thanks to nuclear fusion. And as the atoms, grow heavier and heavier, the process is still basically the same. As 2 atoms combine into 1, they release an enormous amount of energy. The reason why we eventually stop is for reasons that are a little beyond what I can explain. The fusion of iron does not generate any energy. So basically, when the star is old and it's run out of all of its smaller atoms, it starts trying to fuse iron atoms together, and the process no longer generates any energy. So the star starts to die, and it collapses on itself, and it goes supernova. So the crazy and awesome thing about supernovas, you might have thought, iron is only number 26, and there are 92 naturally occurring elements that we know of. So if stars can't fuse anything past iron, where do all of the other elements come from? They come from just this explosion. So as all of the matter that's contained within a star completely bursts, that shock wave that goes through the system fuses all kinds of random elements together, and that's how we get all of the heavier stuff. So basically, after a star explodes, you have this hot soup of just crazy amounts of fusion happening, and you get all these new elements that form. And then slowly over time, all of the soup that's left over from the star's explosion starts clumping back together, and you get all of the hydrogen that was left forms a new star, which is probably smaller than the original star, and all of the heavy elements separate into planets. And that's how our solar system formed. So this is kind of a little cheesy, but if you think of something like gold is a much heavier element than iron. So the best knowledge that we have is that gold atoms were formed during a supernova millions and billions of years ago, which is pretty crazy. So the next time you see anything that's made out of an element heavier than iron, you have to sort of respect it a little bit for the fact that a star exploding is the only way that those atoms came to be.